Hi everyone, we're Group14. Today we are gonna present our group project for MSBD5003, and our subject is performance of clustering algorithms in PySpark. There are three parts in our presentation. The first part is statement of problems. The second part is algorithms and implements. And the last part is evaluation and conclusion. So let me introduce the first part for you. There are three problems in our project. Firstly, how to implement clustering algorithms in Spark. For this question, we will use RDD partitioner and MapReduce to transfer our code in Python into PySpark. And the second problem is how to evaluate the effort made by Spark. For this question, we will record the runtime for each algorithm based on single worker and multi-worker. And the last problem is how to compare those algorithms in Spark. For this question, we set us four criterions to make the evaluation. And after discussion, we decide to use two kinds of clustering algorithms, partitioning methods and density-based methods. The partitioning methods including k-means, FCM, and GMM, and the density-based methods including dbScan, densities, and partition-based dbScan. And for the experiment and evaluation, we will compare those clustering algorithms in groups and in laboratories. Besides, we set up four criteria, including runtime, speedups, scalability, and signups to make the evaluation. And what are the experimental processes for our project? Firstly, data preparing. We select various datasets for clustering to test the scalability of clustering algorithms in Spark. And the second, algorithms realization. We realize those algorithms as functions on laptops based on Python, and then using PySpark to map the Python code to Spark. And second, Spark coding. Firstly, we transfer experimental data set into RDDs with partitions, and secondly, we will map clustering function into each partition. And the last part is output recording. For this part, we record the runtime for different settings on database platforms for single worker and for multi-worker for those different algorithms. And then please let my teammate Cheyenne to introduce the next part to you.
For the partitioning method, a classic algorithm is k-means. The initial idea is to divide n points into k clusters so that each point belongs to the cluster corresponding to the mean nearest to it. And for the distributed program, after we preparing the function to find the closest point as the center by calculating the distance for each point in dataset. For the iteration steps, we first map the finding function to on each data RDD, then to reduce the operation to compute points contained by each cluster. Finally, we do the map operation to compute new centers, and the iteration will not stop until the convergence is met. An extension or an improvement of k-means can be soft partitioning methods, which means points in these methods can be allocated to clusters with different probabilities. For example, the fuzzy means it is operated by adding a membership to the calculation of including a distance compared to k-means, and the membership will be updated in the iteration using updated centers. Another soft partitioning method is Gaussian mixture models, which means each distribution is a Gaussian distribution with weights. The idea is to use posterior probability to update the index in the iteration. Some comparisons can explain some characteristics of k-means. Compared to Fuji means, they both depend on the starting point and distance. The difference is Fuji means replaces the original hard partitioning k-means with membership and only makes it smoother. And compared to Gaussian mixture models, they both can be limited to local optimal solutions, and both need the number of categories to be guessed initially. And the two extension algorithms, Fuji means and the Gaussian mixture models, both are Fuji partitioning methods, meaning each point belongs to each category with a center probability. While Gaussian mixture models, the main idea is a global estimation and optimization process. However, some operations with metrics is relatively difficult to implement in PySpark, while relatively easy in Spark with Scala. The main idea is to use a row vector instead of matrix to map functions with Python. Here are some possible future work for partitioning methods. Firstly, we can use k-means ++ method to select the initial k. K-means ++ can significantly improve the final error of classification results. But in our method, although it takes extra time to calculate the initial point, k-means itself can quickly converge during the iteration, which can actually reduce the calculation time. The second one is to replace including distance with other kind of distance to avoid outliers. Later in the result evaluation part, we can see that k-means is very sensitive to outliers. The third one is that considering the overhead when broadcast membership metrics, we can use matrix operations instead of operations on data points, RDD, to improve fuzzy ones and implement them. Next, my teammate Zhao will introduce the density-based algorithms.
Density-based clustering algorithm based on the idea that a cluster in the data space is contiguous region of high point density, separated from other cluster by contiguous region of low point density. There are two parameters need to be defined, Kc and meaning points. Kc represents the radius of a neighborhood to any point. Meaning points represents the minimal number of points required to form a dense region. An example is shown above. The dbScan algorithm can be abstracted into 3 steps. Step 1. Find the points in the Kc neighborhood of every point, and identify the core points with more than meaning points labels. Step 2. Find the connected components of core points on the label graph, including all lone core points. Step 3. Assign each lone core point into a nearby cluster if the cluster is a Kc number. Otherwise, assign it to noisy. The pursuit code is shown above, which implements 3 steps I mentioned before. Identify the core points, find the connected components of core points, assign noisy points. Similar to the algorithm of dbScan, there are one more step for distance-based dbScan. As we know, the traditional dbScan requires large amount of redundant computation in doing core point searching. In distance-based dbScan, N multi-N matrix will be built to hold all those point pair distance values. That means each distance value computed will be stored into matrix and be found in all one time instead of being computed again. This part shows how our algorithm works. In the left, we randomly generate 3 clusters, represented by blue, green, and yellow. In the middle, we split the data into 16 partitions by KD partition function, which is shown in the GIF. Each partition will be run as a task in the worker, and then partition will be aggregated by aggregator function to get the final result. And in the right, we can see the cluster partitions. There are two main problems in our work. First, how to split data. For partition stage, the general target is to split data points in the dataset into several partitions, so each partition could work separately. We define a method named KD partition in our experiment, which can compute the mean variance to divide the data more evenly. Second, how to aggregate data. For the aggregate stage, the general target is to aggregate each partition we get. We define a method named aggregator to add label value in one partition by maximum label of former partition to guarantee the global consistency. The following section will be introduced by our group member Chen Pongyao.
Okay, thanks Zhao Wei. The result of partitioning methods k-means is on the slide, and let me introduce the details of 4 criteria at first. For each dataset, speedup is using the minimum runtime between 4p and 8p to divide the runtime of 1p. Sideup is using the speedup of total dataset to divide the heart of dataset. And the scalability is on the algorithm's level. It is the average of speedup of those 4 datasets. And you can see from the tables, for D31 and R15 and aggregation dataset, Spark does help to speed up the runtime for k-means algorithms, and when sideup, the help is up. And the Gen dataset has more outliers, so the performance is not good as well. And if just calculating D31, R15, and aggregation dataset, the scalability is 29.8%, which shows Spark also have a nice scalability for k-means when dealing with the suitable kind of dataset. The result of density-based method dbScan for L1 distant for D31 and R15 datasets, Sparse does help to speed the runtime, but when sideup, only D31 is benefited. The reason may be that dbScan is sensitive to the distance between points, so when sideup, the distance matrix will be up as well. And the scalability for those suitable kind of dataset is 19.59%. And for L2 distant, for D31 and aggregation dataset, Sparse does help to speed up the runtime. But when sideup, the help is up. And the scalability for those suitable kinds of dataset is 31.28%, which is better than L1 distant. So finally, we can make the conclusions. There are some similarities between k-means and dbScan when implemented on Spark, including A. It is easy to find that Spark make a difference to clustering algorithms for runtime and speedup if the dataset is suitable. And B. Spark will help to fasten the large volume dataset, which means that the sideup And when size is up, the help may be up for those suitable dataset. And seed need to treat of and seed our experimental prove that we need to find a trade-off between overhead and communications of worker. And also there are some difference between k-means and dbSCAN. For k-means, it is sensitive to outliers, so the result of scan dataset is not good as well. And for dbSCAN, it is sensitive to distance of points, and when using different distance assurance, for example L1 and L2, the effect is different as well. And okay, so these are the whole presentation of our projects. Thank you for your listening.